So we've begun with the Maxwell-Boltzmann velocity distribution, and we've gradually worked our way through to finding expressions for the collision frequency between molecules and the mean free path between molecules. What I want to do now is sort of close the loop on this and come back to basically collisions that might be leading to reactions. But let's start now with what we have done so far. So we have defined a number density, which would be the number of molecules over some total volume. Now I'm going to label these molecules as A molecules, and you'll see why in just a moment when I introduce a different type. And we've also come up with an expression for the collision frequency, which now I'll label as ZA, which was simply the square root of 2 times the number density of A times the cross-sectional area of A times its average velocity. And I won't bother to put a label on that one. All right, so this was great, but it was really just the collisions for one molecule. What if we now want to consider a certain volume of molecules, containing, say, Na different molecules in the volume, and I want to know how many total collisions there are? Well, if there's this collision rate for one molecule, it would simply be this times that for n molecules. So I should have a collision rate that looks something like this. But I should also point out that when I do that, I'm double counting the collisions because every molecule has to collide with another one, so I've counted them for each individual molecule. So when I correct for that, it means that I really need to have this many molecules colliding. So if I were to then develop, I'll call it the AA collision rate that for two different molecules of A, it would end up looking something like this. It would be 1/2 times this. Now, I did this is the number of molecules that are in a volume V, but let's go ahead and renormalize by the volume so that we can talk about an intensive quantity of collision rate. So that means I'm going to have Na divided by V multiplying by this ZA. So I'm going to have a rate that's 1/2 times this number of molecules divided by the volume times ZA, okay, for this total, or 1/2 rho A ZA. But now I'm going to plug this value in for ZA, so I'll have 1/2 times rho A times square root of 2 rho A sigma A times the average velocity. And when I work all this through, I'll end up with an expression that gives me 1 over the square root of 2 rho A squared sigma A times the average velocity. All right, now the reason I go through this to get to this point is not because I'm all that interested in molecules of A colliding with other molecules of A, but I'm interested in what if I have a different kind of molecule there? What if I also have molecules of B and they have a number density of rho B? What would this look like then? Well, I hope it wouldn't be difficult to persuade you that the collision rate of these molecules is going to be similar to this rate that we've written here, except it's going to be the number density of A times the number density of B times a sort of cross-sectional area that's a relative cross-section, and then the velocity. Remember this, we got this square root of 2 because we did a relative velocity for two A molecules, so I've got to do a relative velocity here between A and B molecules. So I'll have an expression that looks something like this, and this is actually an expression I hope that makes a lot of sense. It's going to be related to the number density of each of the molecules in our sample, their cross-sectional area. Okay, so this is just the area that they have to be within each other in order to have a collision. So if you want, you can think of that as being something like sigma AB would be on the order of pi times the average of their diameters squared. Okay, it won't necessarily be exactly that, but it could be something like that. Okay, this average velocity, that relative velocity between them, will simply be the same thing that we've gotten before, 8 kBt over pi, but now with this reduced mass thrown in, where the reduced mass will simply be the product of the A and B masses divided by their sum. All right, so we can get an expression here for the collision rate of A with B. And if we plug in some ballpark figures, for example, we could plug in ballpark figures like the two number densities are on the order of 10 to the 25th, and that was per meter cubed. And our relative velocity, we can say, is something around 300 meters per second. And our cross-sectional area that relates them when they collide is on the order of 10 to the minus 18 meters squared, then we could calculate this average collision frequency would be something like ZAB would be about 10 to the 28th per centimeter cubed second, or it would be 10 to the 25th or so, 10 to the 34th meters cubed second. All right, so it's a pretty high frequency. Now, we're not used to thinking in terms of number densities, and so what we may want to do is convert this into quantities like moles instead of numbers of molecules and liters instead of centimeters cubed. So if we do that, what we'll end up with is multiplying this by 1,000 centimeters cubed per 1 liter and multiplying it by 1 mole over 6 times 10 to the 23rd down here. And when we do that, we'll end up with a value of 10 to the 8th molar per second, moles per liter per second. And this would be our AB collision rate based on this formula that we've derived over here. All right, now let's think about this formula. So 10 to the 8th moles per liter undergo a reaction. Is that right? Or it undergoes a collision. Well, it's a lot faster than a reaction rate would be. So this can't be representative of a reaction rate. So what's the issue? What's the holdup with this? Well, I'll note that this is all the collisions possible between A and B. It also includes those collisions that have insufficient energy, and it may also include those collisions that are not oriented properly, so wrong orientation. All right, so it includes a lot of collisions that aren't going to lead to a good result. We can't do much about this one. In fact, in order to get a handle on orientation, we would really have to do a number of computer simulations to test that out. But we can do something about this one. And in fact, when we do, we find that we can take this expression for ZAB and update it a little bit. And we update it in the following way. We're only going to consider relative energies that are greater than some cutoff energy, and I'll call that E sub A. Okay, so this E sub A is the amount of energy that we're going to say needs to be present in order for a reaction to happen. And what we get from that is when we plug this into our general expression, so I'm using the expression for relative velocity as well, I'll have the cross-sectional area times rho A times rho B times 8 kBt over pi mu AB to the 1/2. And then what corrects for this energy is a factor that looks like this. We'll have 1 over E sub A over kBt, e to the minus E sub A over kBt. So we see that this extra factor is what is needed to convert this into something that might represent a reaction rate. But now I want to, play a little bit with this expression, not for too long, but we have a bunch of factors here. We've got this stuff that's over here, it depends on E, but it depends also on temperature. And this average velocity also depends upon temperature. So we have all of this stuff together, and I'm going to just loop that together and call it K as a function of temperature. So it's some number that's some function of temperature. So I could really write this collision rate as being equal to something that's related to the number densities times this constant, or this function of temperature. But these number densities, if you will, they're kind of related to the concentrations of these molecules. So we could re-express these in terms of moles per liter. And so I would have one that would be sort of a concentration of A and another that would be a concentration of B. Now what I've done here, I don't intend this to be a rigorous derivation of any kind, or even something that necessarily you should write down. But what I'm trying to suggest is there is some motivation for moving toward expressions of this type when we're beginning to talk about the collision rate, the collision frequency between molecules that could undergo a reaction. So this is something that we will come back to in our later studies, but this is, if you will, this is a form of a rate law. So we're seeing already that by considering the collision rates between molecules, we can get to a format that actually gives us confidence that rate laws of this form are ones that could be realistic for describing the kinetics of a chemical reaction.